This question is about amines. It shows infrared spectra of a primary amine, so RNH2, a tertiary amine, which would have no hydrogens, and a nitrile, which would have a triple bond N. Now, remembering with our infrared, we can always ignore, like this part, the fingerprint region. What we're looking for is the difference between these three. So primary amine would have the NH peak. Now, if you look at the data sheet, it will tell you where to look for that NH peak. And so you're looking in and around the region of 3,300 to 3,500. Always looks like a little bit bobbly, and this is an NH peak, 3,300 to 3,500. These sharp spiky ones at 3,000, they're the CHs in them all. And then we can look for a nitrile, and if we look for a nitrile, 2,220 to 2,260, this is our nitrile peak. And then B doesn't have either of those two, because the tertiary amine doesn't have any NHs. So our primary amine was our C, our tertiary amine was our middle one, and our nitrile was A. There are three secondary amines, so remembering that a secondary amine has one H and two R groups that contain 4 Cs per molecule. Draw the skeletal formula. So why don't we put 2 Cs on the left and 2 Cs on the right? What about 3 Cs on the left and 1 C on the right? And then you're thinking, well, 1 and 3 and 1, 2 and 2, 1 and 3. But 1 and 3 is 3 and 1. What we need to do is some branching. So we can put our 3, but with a branch. That, and we've drawn all 3. It says primary amines can be prepared by the reaction of halogenoalkanes with ammonia or by reduction of nitriles. Why is it better to do it from nitriles rather than halogenoalkanes? The problem with halogenoalkanes is that you can get further substitution of the primary amine into a secondary or tertiary amine, and so you will get a lower amount of product, lower yield, and it will be impure. So when made from halogenoalkanes, there is a risk of further substitution leading to impurities whereas with reduction of nitriles, there's only one product. Draw the structure of a primary amine, so that's an RNH2, with 4 carbons that cannot be formed from a nitrile. So remembering that a nitrile goes RC triple bond N to RCH2NH2. So if we're going to have an NH2 on an R group, we just need to not be able to have a CH2 here. So if we think about putting our NH2, what we don't want to do is allow there to be 2 hydrogens on this carbon. So any structure where there's only 1 hydrogen or even no hydrogens would work. So for example, this would work. That's 4 carbons. Or you could have the one where you have CH3, CH3. You put the 4 carbons like this. These cannot be made from a nitrile because the C next to the N doesn't have any hydrogens on it. It doesn't have 2 hydrogens on it. Student dissolves a few drops of propylamine in 1 centimetre cubed of water in a test tube. Give an equation for the reaction that occurs. So propylamine, prop meaning 3, so 1, 2, 3, and then our NH2 in water. And the propylamine is a base, so it's going to accept a proton from the water, make the ammonium ion, and then we'd have the hydroxide ion. And describe what is observed when universal indicator is added. Well, it would turn blue because we've got OH minus in that mixture. Phenylamine, which is a benzene ring with an NH2, can be prepared by reduction of nitrobenzene using tin and an excess of hydrochloric acid. So we're allowed to use H in square brackets as our reducing agent. Now if you count up, you've taken off 2 oxygens, so you'd have to make 2 waters. If you count up the H's, you actually have used 6. Explain why an aqueous solution is obtained in this reduction even though phenylamine is insoluble in water. Well, the point of this is that the hydrochloric acid, in the presence of HCl, the phenylamine would react to give the phenylammonium salt. So if I can squeeze that in here, so we could do that NH3 plus Cl minus, which is ionic and therefore soluble.